Hello and welcome to Chapter 7 on Newton's Law of Gravitation. So before we actually get to Newton's Law of Gravitation, we're going to go over Kepler's three laws of planetary motion. So the orbit of each planet goes around the sun, that each planet goes around the sun is an ellipse with the sun at one focus. Each planet moves so that an imaginary line drawn from the sun to the planet sweeps out equal areas in equal times. And the ratio of the squares of the periods of any two planets about the sun is equal to the ratio of the cubes of their average distances from the sun. So the first two I can go over graphically. The third one is just a prediction that, uh, or a observation that Kepler made when he was looking at the periods of different planets, which states that how long it takes to go in a complete orbit around the sun uh, uh, is uh, the square of those periods is equal to the ratio of the cubes of their average distances from the sun. So uh, this is a mathematical formalism, so we're not going to talk about that as much. But the first two we can talk about. So these were made by Johann Kepler before Newton. And the first one states that the orbit around a sun, of a planet around a sun, uh, is described by an ellipse. So what an ellipse is something so that if you place a bit of string on two points, some distance away from each other, uh, and draw out what that looks like, as you see in the diagram, then it's going to draw an ellipse. So basically what happens for an ellipse to be true, one of the definitions of an ellipse is that this distance here in blue, and then this distance here also in blue. I meant to put that in orange. In orange, uh, when you add them together, those distances are always going to be the same distance. The sum of those two distances are always going to be the same amount as you go around the circle, no matter what happens. So you can see that, or not the circle, the ellipse. You can see that that's going to happen by looking at the strings and seeing that the string is always going to have the same length, and there's always going to be the same distance, the same total distance given by that length of string. So that is what he means when he's talking about circular or elliptical orbits. And then the most basic version of an ellipse is actually a circle. So that's when both of these 2 points, are at the same point. So the same point in the center. So if you do that, then instead of having the sum of the two lines be equal to or the sum of the two lines being equal to a constant, what you have is the one line coming from the circle being constant and just being a circle that goes around. So a circle is a type of ellipse, but an ellipse is not necessarily a circle, in the same way that a rectangle is a type of, or a square is a type of a rectangle, but a rectangle is not necessarily a square. And basically what this tells us is it just tells us the shape of them. And depending on how far apart these 2 points are, then then the ellipse gets wider and wider rather than just being a circle like it almost is for the radius or for the motion of the Earth around the sun or the motion of the moon around the Earth. So just a second. Mouse. Kepler's second law states that the area of a planet for any given time period, the area swept out from a line going through a planet is going to be constant. So let me just describe, show you what that means a little more openly. So I have this line from the sun to the planet, and then after a period of t, or after just some period, it doesn't have to be the period, just some time interval, you go from here to here, and that area that you sweep out is going to be an area. And what they find is that the areas for any point on the for any point along the ellipse, the areas of these kind of triangles, not really triangles, but kind of triangles, is going to be equal, because as you're closer to the sun, what it turns out is that you're going faster. So even though this radius isn't as big, like the radius, how far out you are from the sun isn't as big, you're able to create an equal area to, if you as you look over the course of, let's say, like 3 weeks, that's going to sweep out an equal area as if you're far out for area from E to F, where you're going a lot slower, but you're a lot farther out, so you have an equal area of that you've gone over to when you were closer but faster, as when you're farther out but slower. So all of these are taken over, let's say, 3 weeks. So all of the brown triangle-like shapes are taken over the course of about 3 weeks, let's say. That's not a very accurate answer. It's probably closer to, say, a couple months, because the most elliptical orbits are farther out in the solar system, so they have a lot longer years than we do. But they tend to. I'm not going to say that they always do. But if you look at, like, say, 3 weeks from point A to B, then that area swept out is going to be the same as if you look at 3 weeks from point E to F, which is significantly farther away. This brings us to Newton's law of universal gravitation, which comes from a study of Kepler's law, but is more useful because it is causal as well as descriptive, meaning that it makes predictions about what should happen when you have two objects around each other and applying gravity, instead of just describing what does happen when you look at the orbits of existing objects. So it's given on the left-hand side by the equation that the force of gravitation, the force connecting two objects, is equal to G, which is just a constant, which converts the units from whatever they are into newtons, times mass of an object times mass of another object over r squared. So a couple of things to note about this is that the force on both objects is going to be the same it's going to be pointing in equal opposite in directions, even if one of the objects is much more massive than the other one, or is much bigger than the other one, and is going to cause there to be a smaller acceleration in that object, because as you remember, a more massive object is harder to accelerate with the same force, whereas both of them are still going to have the same force applied to them. It's just that the force is going to accelerate them differently, so that one of them will be accelerated if you have one really massive object like the sun and one smaller object like the Earth or a planet, then what you will see is that the smaller object will be accelerated much more than the bigger object, because and this will cause the smaller object to orbit around the bigger object. Another thing to note about this is that the mass, this force is proportional to the masses of both objects, so it's dependent on the masses of both objects, which is kind of strange because there are a lot of different forces and not all of them have some different proportionality based on different quantities such as charge or charge in the electromagnetic force. But this happens to have the same mass as we talked about when we were talking about Newton's second law and how hard it was to move an object. The other thing to note is that it goes down according to the radius squared, which is the distance between the two objects, which means that the farther out you are, the less the less an object is going to fill the hole of the other object, which is why when an object is farther out in an elliptical orbit, it's not going to be accelerated as quickly as when it's closer to an elliptical orbit, which kind of sort of explains or can be used to intuitively understand Kepler's second law, where the farther away you are, you've slowed down a lot compared to if you're closer and you're being accelerated really rapidly around in your orbit. Before we move on, I want to bring up another couple things. So the first is that the force between two objects in Newton's law of universal gravitation is pointing from one object to the other object, both of them pulling each other towards the center. So I kind of made this assumption that you would know this when I was talking about the relationship between acceleration and Kepler's laws and the law of universal gravitation just a couple minutes ago. But this is something that you can very easily see by thinking about the way that gravity affects something that is going on Earth. So if you drop an object, it's going to be pulled straight towards the center of the Earth, towards the Earth, and in the same way, the Earth is pulled towards the sun when it's going around in an orbit. The other is the ideal of a field. So a quirk of this law of universal gravitation is that because the mass of an object is present in both the force Gmm over r squared, and Newton's second law, then it turns out that acceleration due to a massive object, due to, say, the sun or the earth, is going to be the same for any object that you place around the sun or around the earth. So the acceleration due to gravity, as I said, was constant near the surface of the earth, because near the surface of the earth, the radius doesn't, the distance between you and the center of the earth doesn't change much compared to the distance from the center of the earth. So if you're at Mount Everest and you're at sea level, then that r, that radius is going to be basically the same. So you get constant acceleration for any different object. And this is also true when you do wildly vary r. What the acceleration is going to be dependent only on the mass of the object that's causing the acceleration, so the sun or the earth, and the distance you are away from it. So the field is just a description of how much acceleration, or if we want to think about it another way, how much force is going to be caused by a massive object, by the sun or the earth, depending on where you are in space. So this is useful, and then this comes into contact with Einstein's law of general relativity, where, based on the fact that acceleration and gravity have the same effect, because acceleration is only due to the object that's causing acceleration instead of the object that is being accelerated, or rather than the uh, rather than another quantity like you would see in say electromagnetism, then a gravitational field is going to be the same sort of, is going to follow the same laws as an accelerating object. So one of the things that should happen is that light, instead of going straight, should bend in areas where it experiences high gravitational forces or high gravitational fields, in the same way that light would bend if you were accelerating up in an elevator, where as you accelerate up, the light would, the light that first left your flashlight, if you were pointing it straight forward like you see in this illustration, the light that first left your flashlight would end up lower than the light that left your flashlight later, because your entire body, or the flashlight and you and the elevator, are all moving up at the same time. So it argues that light should bend around high gravitational forces, and Einstein saw gravity as a bending of something called space-time, instead of just as a force that's acting in a straight line between two objects. What he saw instead, hundreds of years after Newton, was that light should, instead of just having this force acting between two massive objects, you would have gravity bending the space around it. So in a way that light would actually bend like it was going through a depression or going close, it was going through a depression in space. So it was like going through a lower area of space. And accelerating as a metaphor, or it's literally changing direction, so it is accelerating, but uh, the space is bent by massive objects, like a trampoline would be bent by placing an object on a massive object on top of it. So he saw gravity as a bending of space-time, rather where space-time is just uh space, and so the distance between objects, which is space, and the time interval between objects, which is time. So it's a combination of those two, and gravity uh causes there to be a bend in that, is the main argument that he makes. And then the way that we can tell that this is true is because we look at stars, and as you see on the bottom picture, an actual star, as it goes past the light goes past the sun, the light bends and it looks like the star is in a different position than it actually is. But if we do the math, if we do the calculations, then we are able to tell that this is something that occurs. Gravity isn't just an interaction between two objects with mass, because light doesn't have mass. It's an actual bending of the fabric of the universe, which I think is pretty interesting and pretty cool, even if it is something that you really have to think about in order to understand. Thank you very much, and see you next time.